everyone, today I am going to talk about the cosets in group theory. Let's start. Cosets. Definition. Let G be a group and H be a subgroup of G, and A belongs to G, H belongs to H. Then the set AH equals to AH belongs to H is called a left coset of H in G, and HA equals to HA, H belongs to H is called a right coset of H in G. G is a group and H is a subgroup of G. A belongs to H and small h is in capital H. Then the set AH. A is multiplied in the left side, so it is left coset. And HA, A is multiplied in the right side, so it is the right coset of H in G. The number of left or right cosets of H in G is called the index of the group, and we can denote it by this. Find example. Find all the cosets of H 0, 4 in the group G. Z modulo 8 addition. G equals to 0, 1, 2, 3, 4, 5, 6, 7 as it is Z modulo 8, and H equals to 0, 4. The following distinct coset of H in G are. We know that addition is commutative, so the right coset and left cosets will be the same. 0 plus H equals to H plus 0. 0, 4. 0, 4 equals to H, we know that. 1 plus H equals to H plus 1. 0 plus 1, 4 plus 1, 1, 5. 2 plus H equals to H plus 2. 2, 6. 3 plus H, H plus 3. 3, 7. 4 plus H. 0 plus 4, 4 plus 4, 4, 8. As it is Z modulo 8, it is 0. So we can find again the H. 5 plus H equals to 5, 1. As 1, 5 and 5, 1 is same in the set, so we can write it as H equals to H plus 1. So 6 plus H equals to 6, 2 equals to H plus 2. 7 plus H equals to 7, 3, H plus 3. So the distinct cosets are H, H plus 1, H plus 2, H plus 3. Therefore, the distinct cosets. Next, the note. We may denote that EH equals to HE. E be the identity element. H itself is a left as well as a right coset of H in G. As E is the identity element, if we multiplied in left side or right side, it will be the same. We can find the H again. So H is itself a left or right coset as well as. Then move to the theorem. First theorem. Let G be a group and H be a subgroup of G. Let H belongs to H, then HH equals to H equals to HH. Then we first prove the H is equals to H. HH equals to H. Then we prove HH is the subset of H and H is the subset of HH. Let P belongs to HH. Then P equals to HH1 for H1 belongs to H. As H1 belongs to H, so we can write P as H1. H belongs to H and H1 belongs to H. So H1 also belongs to H, implies P belongs to H. As we take P equals to H1, so P belongs to H. We let that P belongs to HH and we find P belongs to H. So HH is a subset of H. Let H2 belongs to H. H belongs to H. So H inverse also belongs to H. As H is a subgroup, we know that. H inverse H2 belongs to H. We multiplied H in the both sides. H inverse H2 belongs to HH. H inverse equals to E and EH2 equals to H2. H2 belongs to HH. So H2 is the element of H and H2 is also the element of HH. So H is the subset of HH. From 1 and 2, HH equals to H. Similarly, we can prove it for the right coset. Then it completes the proof. Then the next theorem. Let H be a subgroup of a group G and let A, B belongs to G. Then AH equals to BH if A inverse B belongs to H, and HA equals to HB if BA inverse belongs to H. For the first proof, for the left coset, let AH equals to BH. First we take it to prove it, and then we take it to prove it. So AH equals to BH, it is given. Then for the sum H1 comma H2 belongs to H, AH1 equals to BH2. As we take H1 and H2 as the element of H, so we can write AH1 equals to BH2. Implies A inverse B equals to H1 H2 inverse. As H1 and H2 belongs to H, we can write H1 H2 inverse belongs to H, as H is a subgroup of G. We know if A comma B belongs to H, AB inverse it belongs to H for the subgroup H. So A inverse B equals to H1 H2 inverse, as H1 H2 inverse belongs to H, so A inverse B also belongs to H. Conversely, let A inverse B belongs to H. Then A inverse B equals to H3 for sum H3 belongs to H. As H3 is the element of H, so A inverse B equals to H3. Therefore, B equals to AH3. Implies B belongs to H and B belongs to BH. Thus, the left cosets AH and BH have a common element B. Thus the left cosets AH and BH have the common element B. So, therefore, AH equals to BH. We can prove the second one for the right coset as same manner. Then move to the theorem 3. Let G be a group and H be a subgroup of G. Any two left cosets of H in G are either identical or they have no common element. G be a group and H is the subgroup of G. We can prove it for left coset and right cosets also. H in G either identical. Identical means if A comma B belongs to G, then we can take two left cosets H and BH and it will be the same. So it is called identical. And they have no common element means AH intersection BH equals to 5. Let AH and BH be two left cosets of H. Then either AH, then we have take AH intersection BH not equals to 5 or AH intersection BH equals to 5. We take that it will equals to 5. But to prove AH equals to BH, we have to prove that we have let AH intersection BH not equals to 5. Let B belongs to AH intersection BH. Then P belongs to AH and P belongs to BH. P belongs to H implies P equals to AH1 for some H1 belongs to H. P belongs to BH implies P equals to BH2 for some H2 belongs to H. Hence, AH1 equals to BH2. As P equals to AH1, P equals to BH2. So, we can write AH1 equals to BH2. A equals to BH2, H1 inverse and B equals to AH1, H2 inverse. Let X belongs to AH. Then X equals to AH3 for H3 belongs to H. A equals to BH2 H1 inverse H3 multiply into H3. So BH4 for some H4 belongs to H. We can take it as H4. H4 belongs to H. Then X belongs to H and X also implies X belongs to BH. And therefore AH is a subset of BH. Let Y belongs to BH. Then Y equals to BH5 for some H5 belongs to H equals to AH1 H2 inverse. B equals to AH1 H2 inverse into H5. A equals to H6 for some H6 belongs to H. Y belongs to BH implies Y belongs to AH and therefore BH belongs to AH. From 1 and 2 H equals to BH. From 1 and 2, H equals to BH. Therefore, either it will be the same, H equals to B is identical and they are disjoint. They have no common element. From the Cosets theory, here come an important theorem, Lagrange's theorem. It is very important. Let's prove it. Lagrange's theorem. The order of every subgroup of a finite group G is a divisor of the order of G. Let H be a subgroup of a finite group G. H is a subgroup of a finite group G. We have to remember that it is said finite group. Such that we let order of G equals to n. G has n number of element and H has m number of element. Since G contains finite number of element, the number of distinct left cosets of H is finite. As it is said that G contains finite number of elements, so obviously the number of left cosets of H is finite. Then there exist elements x1, x2, order xk in G, such that x1h, x2h, order xkh are distinct left coset of H in G. Distinct left cosets of H in G. Therefore, G equals to union of xih. It tell that the number of distinct left cosets are the number of distinct left coset of a group is the number of distinct left cosets unions are the group. To show that we can move to the example. Here the distinct coset are H, H1, H plus 2, H, H plus 1, H plus 2, H plus 3. If we take the union of them, then we can find the group. If we can take the union of them 0, 1, 2, 3, 4, 5, 6, 7, then we can find the group G again. So from this we can write that G equals to union of xi h. Thus G equals to xi h union x2h union xkh. Order of G. As they are distinct as a distinct left coset, so their order, the plus of their order, the addition of their order will be the group again, will be the order of the group again. So order of G equals to order of x1h plus order of x2h plus order of xkh. Order of G equals to, we know that the order of H equals to m. So order of xi 1h equals to m, x2h m, m k times m. So order of G equals to n equals to km, k equals to n by m. Order of H is a divisor of order of G, as it is the order of G and as it is the order of H. So order of H is a divisor of order of G. The converse of the theorem is not true. The alternating group A4 is of order 12, but there is no subgroup of A4 of order 6, though 6 is a divisor of 12. The group A4 is of order 12, but it has no subgroup of order 6, though 6 is a divisor of 12. 6 is a divisor of 12, but A4 has no subgroup of order 6. So the converse of the Lagrange's theorem is not true. From this theorem, the second theorem is every group of prime order is cyclic. Every group of prime order is cyclic. Let G be a group of prime order P. The order of group G is P. P is prime. As it is prime, so order of G obviously greater than equals to 1. G has an element A not equals to identity. It has an another element in spite of identity element. Let H be a cyclic subgroup generated by A. Let H be a cyclic subgroup generated by A. Therefore, as it is generated by A, so order of H obviously greater than equals to 1. Since H is a subgroup of G, H is subgroup of G of finite order P, so order of H is a divisor of P. By the Lagrange's theorem, we know that order of H is a divisor of order of G. So order of H is a divisor of order of G means P. By Lagrange's theorem, order of H divides P implies order of H equals to P or order of H equals to 1. As P is prime, it can divide P and 1 only, none of the other. So order of H equals to P or order of H equals to 1. As order of H greater than 1, so it cannot be 1. So order of H equals to P, which is equals to order of G. As order of G is generated by, as H is generated by A, we let that. So order of G is also generated by A. This proves that G is a cyclic group generated by A. It's all about the cosets. Thank you so much.